All right, let's set the context for our next module. We just got done looking at flexural stresses from bending, and those were normal stresses on the cross section from either smiley face or frowny face bending. Now we're going to look at shear in the beam. We learned back in statics how to handle the situation when we had a variety of loads come in and take a little tiny differential element for the free body diagram. That's this thing expanded here, a little dx across there, and we learned about the sign convention for internal forces of the shear and the bending moment. What's shown here on the board, of course, is the American or US designer sign convention. The Europeans do it a little bit differently. There's positive negatives for either one, but we'll focus on the American designer sign convention here. And so we have internal moments, internal shears on the left-hand side, and as we walk our way across to the right-hand side, there's incremental changes in both the shear and the moment. And we learned about what those relationships were with respect to the load back in the beam statics, right? And that the rate of change of the shear was equal to the distributed load intensity, and the rate of change of the moment was equal to the shear, right? And that set up a second order differential equation. In this course, now we're trying to understand how that internal shear varies then, or rather it induces stresses that vary across the cross section. It is not as simple as direct shear, and you just take V divided by A. That would be an average, but it turns out that that's pretty far away from what the actual maximum stress is and how it varies across the cross section. The bottom line on that is that our stress model will turn out to be this thing called tau equal VQ over IB. We know the V, that's just the internal shear. We know the second moment of area, that's associated with the bending axis. But we haven't seen this capital Q nor this little lower B. If this is the cross section here, then what will turn out is that somehow that B is a width parameter that in this rectangular one would be the same no matter where we're at. But in general, that may vary across the cross section. And this capital Q is the first moment of a special area, not the first moment of the whole area, but of only a certain portion of that area. And it is particularly that capital Q that turns out to be, for the person who's first encountering this model, one of the most complicated, difficult things to calculate correctly. And that's why you'll see there's some guided home study problems to help you on the self sense here. That's why it's called guided home study problem that you can go through and practice and get better at understanding what this capital Q is all about. But for sure, we have to be able to pull in our ability to calculate shear anywhere in a beam, our ability to calculate second moment of area, and add to it these other things in order to get to this stress model that we're going to be exploring and developing here in this module.